As always, we thank the School of Social Sciences, Humanities, and Arts and the Gleshko Samuelson Foundation for their generous support. It's my real pleasure today to introduce Suma Rosenberg. He is the Associate Director of the Mixed Reality Lab, which is a term I just learned about earlier today, at the Institute for Creative Technologies at USC. He's also an Assistant Research Professor in the Computer Science Department at USC. He's doing this really fascinating work on turning what seem like bugs of the human visual systems into features, if that's a fair way to put it. There's been some discussion of that on the boards. His YouTube videos have millions of hits, and I'm happy to get 1,000, so that's pretty impressive. So today's going to talk to us about making small spaces feel large, practical illusions in virtual reality. Please join me in welcoming Suma Rosenberg.
Thank you very much for the introduction and for the invitation. So I'm a computer scientist, at least by training, and my talks are often to more technical, computer science-oriented crowds. And so it's a real pleasure to be here because the work that I've been really passionate about is the work that transcends just the technical field and crosses over into other disciplines like psychology and cognitive science and other related fields. So it's especially delightful for me when I get to go and talk to audiences that are from these different complementary communities. So I've been doing virtual reality since I was an undergrad back in 2003. And the first time I put on my first head-mounted display, I became really fascinated by this feeling of being immersed in VR. Virtual reality for me is a kind of magic. It's a medium that you can use to create surreal experiences and transcend what is possible in the real world. Sometimes people have said the holy grail of VR is to make it indistinguishable from the real world, but I think we can actually do better than that. And as a researcher, VR also provides us with a really unique opportunity because it gives us the tools to do controlled empirical study of human perception and behavior that would be impractical or impossible to do in the real world. So it's really the intersection of these two divergent goals, the engineering of magic and also the enabling a deeper understanding of the human experience that is what this talk is all about. So I recognize that a lot of you might not be familiar with VR, or you might have seen it on the news, but haven't necessarily been deeply following what's been going on in VR for the last several decades. So I'm going to start out just to put all this work in context by giving you a brief kind of whirlwind introduction in the history of VR to put all this work into context. And then that's going to be about 15 minutes, and then the remainder of the talk I'm going to focus on the fun stuff, which is what I like to call informally hacking human perception. And there's several different illusions that I'm going to talk about today. First, motion illusions, spatial illusions, and haptic illusions. And some of you who have read the paper that was sent around before, one of those illusions is spatial, but there's several others I'm going to be talking about. So let's start first with a whirlwind tour of virtual reality. So if you've been following the news in the last year or two, and you're reading blog articles, you might think that VR was just invented. Like, what is this thing? It just suddenly, everyone has just came out of the blue, and we're all just discovering this for the first time. Well, it turns out VR's been around a very, very long time. So actually, the first kind of work that could be recognizably in this area dates back to hundreds of years. This is a Wheatstone stereoscope. So this is actually kind of one of the first apparatuses that could create a synthetic 3D experience. It was just 3D images, but they figured out how to do stereoscopic images and then align mirrors with a divider so that when you look down the divider, it's reflected off the angled mirrors and you see the two images which are then fused into 3D. This is actually the fundamental principle that all of our head-mounted displays today still use. However, we've replaced the mirrors now with much more compact lens assemblies. The first VR sort of simulator actually dates back to the 50s, before the PC era. So there was this thing called Sensorama that was actually, this was an experimental film device that had things that we still dream about having in VR today. Sound, vibration, the feeling of wind, and even smell were all integrated into this device that was purely mechanical. There was no computer controlling it. So really ahead of its time, but it shows you kind of the vision that people have even early on VR had these high expectations for what it could do, and we can't even do a lot of this today. Vibration, wind, smell, all these kind of things are still really lacking by today's standards. Fast forward now to the 60s is when we start to see the first head-mounted display being developed. Head-mounted loosely because you can see it's actually mounted, was tethered to the ceiling. So now it's very useful as we talk about VR and see where VR is today to look at what a graph called Garner's hype cycle for emerging technologies. And this has actually been applied to across a wide range of technologies. And it really, what it describes is kind of the hype cycle and public opinion and eventual adoption of new technologies. So what usually happens is they start with a trigger, something happens with technology. There's what's called a peak of inflated expectations, where everyone has incredible hopes for what this technology can do. It can do meet absolutely none of those expectations, and then you fall down into the trough of disillusionment. People get, throw away the technology or don't want to, pay attention to it, and then eventually, maybe decades later, you climb up the slope of enlightenment. It gets good enough, and then you start to be productive. But that plateau of productivity really never hits what those expectations are. This actually fits the model of what happened with VR perfectly. So let's talk about the technology trigger. The first HMD came out in the 80s. That was wearable. And so you started to see now, this is the technology trigger because now you can start to actually put devices on people's head and give them VR experiences. So you start to see the first VR companies. VPL was the first, and then several others were founded in the 1980s actually selling these devices. So even back, a good 30 years ago, we could buy head-mounted displays. But then what's looming here is this peak of inflated expectations. VR caught the public eye. There was this very famous Scientific American article, and then of course movies started to popularize VR, Lawnmower Man, and later The Matrix and other movies. The hype was far beyond what the technology could do. And then there were some real commercial failures that kind of brought everything crashing down. Sega tried to create a VR display. Not many people know this. They released it, they advertised it at the Consumer Electronics Show, but they canned the project halfway through development because they realized this is too hard. Nintendo actually put a product out, but it was a commercial failure and disappeared shortly thereafter. And VPL, that first company that was founded in the 80s, went bankrupt. So what really happened was VR fell into this very long and slow cycle of disillusionment where it was considered a dead field. And it was actually considered a dead field when I started doing this back in 2003. And I told a colleague that, and he said, "You started this as a student when VR was dead? What's wrong with you?" And I said, I guess I just really like the challenge. But so this story does have a happy ending though. So around 2010 is when I moved to USC, got my PhD, and if you look at around that era, something's going to change. This is kind of two of the typical displays that you could buy if you wanted to do VR. And if you look at the cost of these displays, anything that could do anything with a reasonable field of view that would feel immersive was in the range of $25,000 or higher for a single unit. Anything that was lower cost, and these are much higher cost than most people would reasonably afford in the home, had like 40 degrees field of view. Let me give you an idea of how big of a deal field of view is for virtual reality. This is a field of view mapped onto the human retina and the visual system. That's about a 40 field of view, and the blue indicates kind of the full range of human vision. So it's like looking through a tiny little distant window. Really falls short of that magical feeling that I talked about earlier, creating an experience that feels, even not even real, but even surreal. So when I got to USC, I had the opportunity to start working with one of our really unique displays. Only a couple of them exist in the world, called the Y5. And this one could do 150 degree field of view. So if you look at this, the difference between this and this, 40 to 150, it's like there is no comparison. Once you see wide field of view virtual reality, there is no going back. So if you look at this, anything that could do anything even approaching that one was $45,000. Anything approaching that was in the $40,000 to $60,000 range. So far beyond anything that would ever be useful or applicable to a broad range of people. So how do we get out of the slope of disillusionment and move on, trough of disillusionment, move on to the slope of enlightenment? Well, something's going to happen right around 2011 that's going to change everything. So one of the things that really, the driving force behind all of this was smartphones. And smartphone displays were getting larger, bigger, lower cost, higher resolution. And at the beginning, it seems obvious now with all this kind of stuff with Google Cardboard and smartphone VR, but back then it wasn't obvious. And so we had the idea, what if we just take a bunch of lenses off of an old display that's been gathering dust for the last 20 years, put it in a wood case and put 2 iPhones behind it, running some 3D stuff. What would that look like? So we built what we, at least to my knowledge, one of the first smartphone-based HMDs, prototypes, and we brought it around to VR conferences. We showed it to people. What do you think? And there were all these problems with it, but it was, you look through it and you're like, huh, this actually looks kind of better than the $40,000 display that I had in my lab. So it was very promising. So with that, we kind of moved forward and we hired a little upstart named Palmer Lucky, a teenager who was a hobbyist building VR displays. And he started basically building what we called Franken HMDs, which were basically cobbled together from parts on eBay and old HMD parts, held together literally with tape. But these were kind of the early prototypes that led to these low-cost consumer head-mounted displays. And then we also started to experiment with the idea of, well, if we can leverage the phone, and we can, all that computing power is already on your device, then what is the rest of the VR display? You can even build it out of cardboard. So this was sort of our early prototype of a foldable, disposable VR display. We brought this to a conference, we made hundreds of them, gave them out to people for free, and it really kind of changed, I think, the way that people were thinking about the cost and the economics of VR. So we open sourced all of this. So actually, this is more of kind of a historical perspective now because consumer VR has now become really just prevalent. But we put all this out for free, and you can still download these designs, 3D print your own head-mounted display at home, or 3D print your own smartphone or tablet VR display. But there's only so much that you can do with open source. And so we started to think about, as academics, we put this all out there for free, but not everyone has a 3D printer. So Palmer, at this point, he decided, you know what, I'm going to go for it. I'm going to go run off and start a Kickstarter. And we all said, good luck, that's been done before. There's no way that's going to work. Turns out he raised $2.4 million, fast forward 2 more years, he's on the cover of Popular Mechanics and Time, and Facebook acquired the company for $2 billion. So joke's on us. At the same time, about the same time, Google really popularized the idea of this foldable cardboard display. And the thing about, as far as we know, this was a coincidental co-invention 2 years later. I believe they were not even aware of our work with FOV2Go. But one thing that they've really done, which is more than we as academics could do, was they created a platform and popularized that platform. So it's less about the actual cardboard, and it's more about this ecosystem that Google is now creating to enable people to do mobile VR, which is actually really cool. So now, we've got all these displays. They're coming, there's, for the first time in history, there's major tech investment in virtual reality, and the cost is down, and now we can actually start, it's the barrier to entry for someone who's in the cognitive sciences or someone who's in the humanities to start working with VR is very low because the hardware is inexpensive, the software platforms are there, you can buy a system off the shelf and have all the software tools to use them, and people are getting trained on them and can learn them very rapidly. So for the first time really in history, VR could be a broad mainstream phenomenon. So I would make the argument that we're climbing up the slope of enlightenment. I don't think we're quite there yet, but I think the trajectory is good. So what is necessary then if we want to fully climb out of this trough and then be productive with VR? What are the problems that remain to be solved? And that's kind of the context that I'm going to present the rest of this work, is sort of thinking about the problems that need to be figured out if VR is really going to be successful. And I'm going to focus on one of these problems, which is really kind of what has been my focus for many years, even before all of this, which is the problem of locomotion or movement. This is one of the fundamental challenges for any sort of virtual reality system. And if you look at a lot of the commercial applications that are coming out, especially in the game community today, they look like this. They're seated use, they're people using controllers. And that has a use. You can get a lot of interesting things you can do with a controller, but for me, I've been doing this now for over a decade, and that magical feeling that I talked about, wanting to create experiences that truly stands transcendent, for me, I can't get that with a seated VR system. I need to be able to get up, move my body. I need to be able to touch things and interact with the world as if it were real. And so that's a real problem. That's hard. So luckily, there's now these systems coming out like the HTC Vive, some of you may be familiar with it, that now do tracking on room scale. So this is really good because now we can do tracking in the size of a room or a larger space, and you can actually walk around. But there's a problem here, is that what happens if I want to go through a large virtual world? I don't want to be limited forever to virtual reality experiences that are one single room. I want to go through virtual cities. I want to go through infinite landscapes. So how do we solve this intractable seemingly intractable problem of space? So this should be pretty obvious, right? Like, you're standing in this room of physical size, you move around, you want to go through a large virtual world, at some point you're going to run into a wall or rock outside the boundaries of the tracking space. So fortunately now, I'm going to talk about the solution to this problem, one potential solution, which we call, again, hacking human perception. And the first type of illusion I'm going to talk about that is applied to this is a class of motion illusions known as redirected walking. The key here is that we're interested in this as a perceptual phenomena and to study it, but also it's applying it to solve this fundamental challenge for VR. So redirected walking is something that was initially introduced back in 2001, so I didn't come up with it. But it was initially formulated as the idea that we can subtly employ some sort of discrepancy between the mapping between your physical motion and your virtual motion. And if you do that in the right way, hopefully users won't perceive it and they'll walk back over the path in the real world that they've already walked through. So let me give you an example of how that might work. In this example, you're walking through a virtual space, you're running out of room, and now you're going to rotate your body. And in this example, you rotated 90 degrees virtually, but 180 degrees physically. And then you can continue walking after the rotation is complete, back through the space that you've already gone through. Now the key here is that the rotation doesn't happen by itself. It's tied to your own body motion. So it's an amplification or a multiplication factor on your own body movement. And that's the key to making this work. Same thing with curvature gains. This is another way of doing it. In this case, you actually walk forward, and there's a very slight rotation that's applied as you move forward in the forward direction, and this actually tricks you into correcting for it and slowly walking along a curved path while perceiving you're walking straight. Oh, sorry, perceiving you're walking straight while physically walking along a curved path. And then finally, there's translation gain, which is essentially downscaling or upscaling the magnitude of your forward movement, so you can cross greater virtual distances with smaller physical steps. So what is the perceptual phenomenon at play here? So it turns out that when your vision system and your vestibular sensation are usually coupled. However, in VR, this essentially illusion decouples them. And it turns out that vision is a sense that tends to dominate over other senses when they're in conflict. So basically, your body believes and your brain believes what it sees over what your vestibular system, your liquid swirling around in your inner ear is telling you about your body motion. So, with an asterisk, so long as the magnitude of that motion is within what we call a certain perceptual threshold. And there's been a lot of work before I started doing work in this area that has attempted to kind of do psychophysical experiments to estimate what is that threshold for how much we can redirect people. And these are some numbers just out of the literature. There are competing numbers about that depending on the experimental measures of who's doing the measurement and how they did the task, of course. But these are some number guidelines, like 50% amplification of rotations, 20% dampening rotations, and this is imperceptible. And the key here is it's a perceptual phenomenon, not a cognitive phenomenon, which means it's below the conscious level. It's actually something that's more fundamental about our brains and our bodies than just, can I distract someone and will they notice? This is actually, am I capable perceptually of noticing the difference? So what are some research questions that have been asked in this area? So the one that I just said, asked was, how much redirection can we apply before it becomes acceptable? And the answer there is a decent amount, quite a bit. A related question that people have started asking was, how much redirection can we apply before it becomes noticeable? This is actually a different, though related question, because this is now a cognitive function, because you can actually distract people, or you can not tell them, or you can prime them in different ways, and then they won't notice it, even though they could theoretically perceive it. So the answer there is we can do even more. So those perceptual thresholds, really, practically speaking, are probably conservative. But the real questions that I started when I started doing research in this field that I wanted to ask were to go beyond just the question of perception, or is it perceptible? Because we know that within a certain magnitude it is imperceptible. And to look at how redirection actually impacts the experience. If we're going to actually start using this and studying it, we should ask questions about, like, how does it impact my spatial understanding of the world around me? How does it impact my ability to actually do a task in a virtual environment? How does it impact my behavior and the way I move? So if there's a theme to a lot of my work, it's that these are the questions that I wanted to focus on, trying to come up with new ways of objectively measuring the impact of these types of illusions on people beyond just this, this question of perception. So I just wanted to go back to that video that I showed before, which is an experience that we put together for the stop motion animation gallery, and look at how effective redirected walking can be in an actual environment. So in this environment, they're walking through a virtual guided tour of a gallery, and the bluish-green rectangle here is the physical space. And we put in that couch there as a marker so to see the scale, that really you're going through this whole hallway and this whole larger space, but really in this example, you're actually walking back and forth in front of a couch. So you can really use this stuff in mind-bending ways. Okay, so now I want to talk about some of the experiments that we've run to kind of get at these new types of questions that hadn't been asked about redirection before. So this is one of the first studies that I ran as a postdoc at USC. And so in this, I wanted to ask that question of, how does this impact my spatial orientation in the virtual world? So I devised this pointing task where they were asked, they put on an HMD, and then they looked outside the HMD at a real target. So they saw a target that we were actually moving around while they were wearing an HMD. People were running around placing targets in space, and they were pointing at it, and we were tracking where they're pointing. And then they put on the HMD, and they see another virtual target somewhere else in the virtual world, and they point to that. So they're basically registering where I think these targets are. Then we're going to do some redirection on them, and essentially see where they think the targets are after we apply redirection. So first question I wanted to ask was, how did this redirection impact their spatial orientation in the virtual world? So if we look here, this is what they did. They pointed at a real target, pointed at a virtual target. They now go through a virtual world. This was continuous, but for the purposes of the example, I'll just do the animation now. They, at the end of walking through whatever corridor they had been redirected by a total of 90 degrees. So at the end of that, would they point back where that virtual target was originally observed to, or would they point to the virtual target at a 90-degree offset, as if the virtual target that was now invisible had been rotated along with the virtual environment? Were they essentially pointing at a read target as if it has been redirected along with the virtual world? I expected that they would. Oh, whoops. What happened to my graph? There it is. Okay, and that was that hypothesis was correct. So this is angular error that we measured from that pointing task. So basically, lower is better. So that means if it's a low error, that means they're pointing very close to where the target was. This was their pointing to the redirected target, the target after the redirection had been applied. This type of error is about 36 degrees. In other pointing tests of VR, this is consistent. So this is about the error you would typically see if they were pointing at a target in VR. This was the target error they saw in the original target, where the target actually was when they had first observed it, and it's about a 90-degree offset. So this is a pretty strong case that strong evidence that they were essentially their reference frame for the virtual world was being rotated along with the redirection. And now I'm going to show you the next question, which was, I think, the more potentially interesting one, which is, what happened to that target in the real world? Did they point to where it still was in the real world, or did that also get redirected along with the virtual world target? Essentially, what I'm asking here is a fairly subtle question. But so to get into a refresh your memory, they were redirected. There was a real target that they had observed before they even put on the display. And then there was a virtual target. A real target that we had calculated what its position would have been had it been redirected with the virtual world. What I'm really asking here is the question is, can we maintain both of these reference frames simultaneously? Can you hold on to a real world reference frame or a virtual world reference frame? Or is manipulating that virtual world reference frame basically cross over into the real? And here's what we found. We basically found very similar results to the virtual target test, where they were pointing to real targets as if they had been redirected along with the virtual world. And this settled a long-standing argument that I had with another researcher in the lab, where he claimed that he could hold two reference frames at once, and I said, no, I don't think that's going to be shown in the data. And he said, okay, I think in the end we've settled this argument. So I think that was one of the really interesting first results that we started to see when we looked beyond these questions of perception and looked at spatial orientation. So now I want to talk about some other types of illusions beyond just the motion illusions that I just presented. And for this, the first one I'm going to talk about is from the paper that we sent around. So those of you who read it, this will seem familiar to you. And for this, I've always had an interest in psychology, even though I come from computer science. I've taken psychology courses, been really interested in all psychological phenomena. So I was sitting in a talk one day at a VR conference and on redirected walking, and I had an idea because I've recently been thinking about change blindness, which I had seen in my psychology course. And I said, what if I apply this in VR to solve the same problem? So those of you who are unfamiliar with change blindness, let me give you an example. So everyone go ahead and take a look at this image, and then I'm going to change something. Does anyone see what's changed? Feel free to shout it out if you do. I'm going to make it really easy for you. So that interstimulus image that I flashed up there was enough to disrupt the motion between the two images, and this is universal. That's very, very difficult because the human visual system uses motion to detect changes to updates to visual scenes. So this has been long studied in psychology and is nothing new, but no one had thought about trying to apply this to VR to solve this locomotion problem. So here's how we ended up doing it. So in this example, I was walking through a virtual room, and you have to forgive the programmer art here. We're computer scientists, so a lot of our rendered environments may not look pretty, but they're experimentally sound, I promise. So what happened is they're going to walk into the room here and then into the corner, and in this test they were asked to look at the images that were appearing on monitors on the virtual desk. So they're going to walk to that desk and watch what happens to the map on the upper left when they walk close to the computer. So what happened there was that the door essentially swapped off the wall, rotated 90 degrees, and then the entire hallway outside of the room and the entire structure of the virtual world outside of that office was basically restructured to be 90 degrees offset. And you're going to basically do this over and over and again, an infinite number of times, and essentially walk through an infinitely large building, so long as there are these corridors and turns and things like that, and architecture you can manipulate behind people's backs. So we did this in a study, and what we went through 12 of these rooms and through a large experiment. We actually did multiple experiments on this, a total of 77 people, and only one person out of the experiment noticed, and we were not expecting that. We were expecting mixed results. Some people would know, some people would not, but I had all these batteries of tests to try and tease out through leading questions, and try to come up with new mechanisms in our second study of trying to get at questionnaires that get people notice. And it's really hard to analyze statistical data when basically everything's zero. So, but this was actually a really, really cool result. And then the other thing that we found in running these studies was that even though these architectures were being dynamically updated and changing, and actually was never consistent globally consistent, these spatial inconsistencies in the end get resolved because people try to draw cohesive maps. So overwhelmingly, when we asked people to draw maps of the environments, we got pictures that looked like the office building that we were trying to model, even though these environments were being manipulated and the architecture was completely not possible to represent in the on paper. So this was a really, really cool result, and so I started thinking about other ways we could use this. So this wasn't in the paper I sent you. So this is an example where we're using that same type of illusion, but we're pairing it, we're essentially doing what I'm calling the infinitely long road. And so to really show off why this would be cool, is that we trucked in 1,000 pounds of gravel into the lab, which I would not recommend to anyone. It was a huge mess. I'm still cleaning up after it. But basically, when you walk out onto that road, you get that feeling of gravel, that physical sensation of stepping onto a different surface. And then when they walk back, you see in the room here, you'll see the map get updated in just a moment. They look in some crates. This was a search scenario. They'll turn around, they'll exit, and now that door has been offset. And we've essentially moved, this one was more drastic. We've essentially swapped the whole outer door from that left side to the right side and ended up changing. They entered in this room here, and they exit out the building there. That's a 30-foot difference. Again, people tend not to notice. I've demoed this with hundreds of people informally, and every now and then someone notices, but it's by and large it's incredibly effective. And the other thing that's really cool about this is a departure from those motion illusions I showed you, which are continuous in nature. You can't pair that with a road because you can never predict how much the world is going to be rotated. But these changes are discrete and predictable, so I can place physical objects and map the illusion onto physical objects like a road. So I'm going to go ahead and now move on to the next illusion. Whoops. So you can't tell, I get inspired by other things. So psychology, and now I'm going to talk about a different one. And I got inspired by basically an illusion from science fiction. So we left doing these change blindness studies with the conclusion that, man, we can really, really manipulate people in VR and mess with their perceptions of space way more than anyone thought we could. So what other cool things can I try? So I'm a fan of science fiction, and so how many of you are familiar with the BBC television show Doctor Who? Okay, great. So for those of you who are not familiar, he has a time machine, which is about the size of that. It's just, about the size of a phone booth. And when you walk inside, and inside it's actually enormous. And there's always this moment when he brings companions in, and they walk inside, and they're like, oh, it's bigger on the inside, and they make a joke out of it. But I wanted to feel what that felt like. So I was like, well, in VR we can do that. So here's the experimental test environment that we came up with to try and get at this illusion. So in this environment, again, this is an office building. You can see I reuse kind of the same textures and like a desk type of thing from the last experiment. In this environment, they walked into one room, they exited, walked down a hallway. When they're walking down the hallway to the next room, the first room is subtracted and the next room is added. And so if you overlay these two on top of each other, it's a severe violation of Euclidean geometry. So clearly these would be existing on top of each other in the real world. So I like to call this illusion impossible spaces. And so what we can essentially do when we're measuring this, I wanted to ask the question of how much impossibility can we get away with, and the way that we chose to model that numerically was look at overlap levels. So this is 0% overlap, so this is a totally possible building. And then what we essentially do is manipulate the level of overlap, moving them closer together. So that's probably about like a 75 or 80% overlap in square footage of the two rooms. And so basically, when you get that much overlap, they're almost like right on top of each other. So I ran an experiment where he tested all these different overlap levels from 0 up to 75%. Okay, so the graph I'm going to show you now is basically what happened when people went through a battery of trials where they were presented with what's called a two alternative forced choice, where they're essentially forced to choose, go through an environment and then choose, is this an impossible space or a possible space? And they were explaining kind of how this illusion works. So they were already primed to what this illusion was, but they were asked to judge whether they just walked through something that was impossible or possible. On the vertical axis here, you see the probability over all the trials that we did many of them, that they would respond impossible versus for any particular overlap level. So here you see 0, 15, 30, 45, 60, 75% overlap is almost completely on top of each other. And so what would we expect to see in this graph? Well, first we would expect to see that they're going to follow some sort of basically curve. That 0, they're going to be, okay, very low chance of it responding impossible. And then by 75%, we expect to see, oh yeah, most people will probably generally be able to detect that as a huge amount of overlap in the space. And what we find is, essentially, what we look for there is 56% was our threshold, what we call our threshold, because that's the probability at which it's 50%. So that's flipping a coin, that's chance level. So anything at 56% or lower probability, they're worse than flipping a coin at being able to detect this illusion. So that's a pretty strong indication that we can get away with quite a bit. But again, remember, I wanted to ask these questions that go beyond the people notice. So I wanted to ask a question of how do people perceive distances and understand this space even though it's impossible? So I devised what's called a distance estimation task, and this is actually something that's been done very extensively in VR because people tend to underestimate distances in VR displays. I won't get into that today, but it's actually a huge topic area that's been studied for many years. So there's a lot of established mechanisms by which people study distance perception that we can then use in this case. So in this case, after they went through a trial, I would ask them, they'd be standing at the second desk, and then I'd ask them to look back through the wall to the room that they just came from, and imagine where they were standing when they were at that first desk. So then the display goes completely black, and they're asked to walk and stop at the point at which they were standing when they saw that first desk. And they had to trigger the desk, they had to be standing right on top of it, so it was a fairly precise location. This is an experimental metaphor called blind walking, and again, it's been extensively used to study distance perception. The caveat, or the special sauce here, is that, of course, when they were overlapping, the actual place that they were standing was not, in fact, through the wall, in some cases, and all the way far away. In the 75% overlap case, it was actually only like a couple steps away. So the question that I wanted to ask was, were they going to walk and stop to where they actually were? Or would they essentially correct for the overlap and walk longer amounts of distance as if those rooms were actually side by side, even though they were not? So here's what we found. So on the vertical axis here, we have walk distance as a percentage of the actual distance. So if they were 100% accurate to where they were actually physically standing, we would expect the data to follow this horizontal guideline, 100% accuracy every time. Again, different overlap levels from 0 to 75. The red predicted line is what we would predict if they were essentially correcting for that correction. So at every overlap level, that red line determines where the target would have been if the rooms were displaced, put exactly side by side, and they walked at overestimated distance. So here's what we found in this data. And again, the data is so clear-cut, you don't even need to statistically analyze it because it really perfectly fits that model. And so this was one of the more exciting things that I think we found, because it actually showed that even in the 75% overlap case, where most people very consistently were able to say and responded, this is an impossible space that I'm standing in, they still behaved and walked as though they were in a possible space. So that was a really good result. And so I want to close this section of talking about the illusions with kind of a really interesting paper that we did to try and kind of inspire game designers and other people to how we would actually make use of these types of illusions in a kind of large-scale virtual environment. So this is actually a procedurally generated environment, and we're using what I call a type of impossible space that I call twisty hallways. So the idea here is only the rooms in this environment were pre-modeled. It was designed as like a virtual exhibit or museum. So you go in and you're looking at different exhibits. When you choose a door, and you can choose any door, a twisty hallway is procedurally generated on the fly by the game engine. And basically based on where you are and where you want to be to get into the next room, it basically generates some twisty corridors that go back and put you back in the center of the space. And you can basically do this infinitely, and it's really flexible. So again, we go through these environments, and you can, people get a sense, I think, if you do this for over hundreds and hundreds of feet, that I'm walking really farther than I thought I should. But it's hard when you ask people, do you know how we did it? And we get a lot of guesses, but like the twisty hallway phenomenon just seems like it's a really powerful metaphor because people tend to just follow hallways. You don't necessarily think they're going to twist back it up. So we think that this could actually, I have not seen anyone yet use this in any sort of game type environment, but I think it could be really an interesting game mechanic. It could also be used, very useful for things like educational applications where the spatial layout of the environment doesn't matter, but maybe you're seeing different virtual exhibits and you're trying to get some sort of educational interaction with some sort of content. So this would actually be a really good mechanic to use because it doesn't use those motion illusions. Okay. And then finally, I want to very just briefly tease you guys with a new illusion that we call haptic or body illusion. And so this is this wasn't exactly my work. This is the work of my PhD student. He went on internship at Microsoft Research. And so this was just published earlier this year. And so this is applying the same concepts of redirected walking, but now we're going to do it with reaching. So what's happening here is he's reaching out, and this is like a Minecraft-style cube blocking, cubes, and they're basically stacking, and they're trying to build up a tower of cubes in a specific formation. As he reaches out, you can see his arm is being live digitized by a Microsoft Connect, so he's getting a virtual representation of his arm that he can see. But notice he's just reaching for one cube over and over and over, and he's stacking it and moving it around in the desk. So these same types of illusions that we apply to the whole body moving through the space, we can apply as your arm reaches out and actually give you the sense that you're stacking, not moving it in a differently in horizontal space, but also vertical space. So you can pick up the one object, put it back on this desk in the same height that it was, and feel that you're stacking things vertically. So it's a really, really neat illusion, and so I expect more work will come out of that. So to summarize, in virtual reality, it's really powerful because the laws of physics don't have to be consistent with the real world. They can be whatever we as designers want them to be. And the really cool thing is that human perception will adapt and recalibrate. And actually, now I get asked this question a lot about recalibration, about long-lasting after effects. Other studies have shown that this recalibration occurs very fast, on the order of 3 to 5 minutes. And then you recalibrate back to real world in another, again, 3 to 5 minutes. So given a little time to adapt to a completely foreign set of physical rules and laws, the human mind is very adaptable. So leveraging these observations, we can really start to create magical, surrealistic experiences. Things like walking into an environment where the world might radically change around you, or walking into a room that's much larger on the inside than it could ever possibly be as viewed from the outside. And also, especially since I'm speaking to people in cognitive science, it's also a really powerful platform for studying the human experience. And hopefully I've teased you with a few results. Again, I'm a computer scientist who likes to pretend he's a psychologist, but in the hands of people who are specialists in this area, you really do some deep dives into some of these illusions and these perceptual phenomena at play. And finally, in the spirit of I'm an academic and I like to give things away for free, if any of you have access to VR and are interested in these types of illusions, we have an open source toolkit available that uses all the motion illusions that I presented earlier today. So that works with the Rift, the Vive, custom VR setups. It's based on Unity 3D, which is a very popular and prevalent toolkit for a game engine for developing VR content. It's open source, free to the community. The link will be on my final slide. Feel free to download and let us know what you think. Of course, this was the work of not just me, many graduate students, postdocs, and engineers at the MXR lab, a subset of which are shown here. And with that, I'd love to take questions.